So this continues the second segment on chemical and physical changes. Today we're just going to be focusing on physical changes. In the last set of slides, the last set of notes, you saw the differences between solids, liquids, and gases in terms of the movement of energy. We talked about that in the process of changing from one state to another, what direction that energy flow is going. Today we're going to look at these changes in phase from a molecular standpoint. So there's two factors that really determine the state of matter. We're going to look at kinetic energy, which is really temperature. Temperature is a measure of the average kinetic energy within a substance. So remember, kinetic energy has to do with motion or movement, and heat itself is the flow of energy from one body or system to another due to a difference in that temperature. And heat always flows from warmer objects to cooler objects. The other factor in determining state is the intermolecular or attractive forces between atoms and molecules. This feature is negligible in gases, which we'll see here shortly, but it's very important in solids and liquids. So this is your big idea. These are the two things that we're going to explore a little further in this set of notes. So in solids, what you see here are two different molecules of water, and I'm not so concerned that you understand what these symbols on the screen mean, as long as you know that there's two molecules of water there. With solids, we see that the kinetic energy within the molecules is not strong enough to overcome the force of attraction between the molecules. So essentially that force of attraction is stronger than the kinetic energy, and that force of attraction overwhelms any energy that would allow those molecules to move past one another. Okay, so the attraction draws them closer together. We also see that solids have a fixed volume and a fixed shape. What's important here is that not only that you can distinguish between a solid, a liquid, and a gas, but you need to be able to understand how these different states of matter respond to their environment. And so a solid's shape will not change no matter what kind of container you put it in, and the volume also remains the same. And this diagram here on the left shows just that solids typically have a repeating pattern for those molecules, that they're arranged very tightly in a repeating pattern. There is kinetic energy there. You can just kind of barely see that these guys are wiggling or vibrating in place. But again, that attractive force between the molecules overcomes the energy to move around. And I've got a link here. We'll see if this works. I really like this particular animation because it does show the substances inside a container. There are some spelling errors on this page, so kind of look past that. But with the solid here on the left-hand side, we see that as that container is shifting around, the solid maintains its shape. The solid also maintains its volume, and volume is that amount of space that it's taking up. So we'll go back to the slideshow here. So with liquids, we find that the molecules do have enough kinetic energy that they're able to slide past one another. This is just a cartoon to kind of help you picture this or visualize this. If you're in a crowded department store, or even say a crowded theater, or say the halls of this school in between classes, there's enough energy, you have enough energy to slide past people and move past people, but you're often bumping into people as you're trying to move through. So liquids do have enough kinetic energy to start to move around and pull away from the other molecules, but that force of attraction is still strong enough to hold those molecules or atoms close together. So I would almost say that kinetic energy and the attractive forces are very close in terms of their value, and the kinetic energy is high enough, there's enough vibrational motion within those molecules to allow them to move past one another. When we look at liquids in terms of their containment, liquids will have a fixed volume, but they do not have a fixed shape. So what that means is that a liquid will take the shape of its container, but its volume will not change. And If we go back to, if we go back to that animation, we see that with the motion of this container that the volume stays the same here. It's the same amount of space being taken up. However, the shape of that liquid changes as that container is moved back and forth. With gases, here we see kind of the opposite of solids. The kinetic energy actually overwhelms or exceeds the attractive force, and so gases, the molecules and atoms, have no attraction or attractive force toward each other. They have so much kinetic energy that it overwhelms that attractive force, and the speed of these molecules is too fast, and so they're not able to be attracted to each other. With gases, we find that they have no fixed volume and no fixed shape. So what this means is that a gas will take the shape of whatever container it's in, and it will also fill that volume or that space that's available. And if we go back to our animations here, and then if we look at these contained, you can see that the gas here we have in an enclosed container, and that the gases completely fill this space. They completely fill that volume, and they have very little attraction to each other. So this table pretty much just sums up some of these properties of gases, liquids, and solids in different states. With gases, we see that they take the shape and volume of the container. So whatever that shape of the container is, whatever the space is, that gas is going to occupy it. It has a very low density, but it has a very high compressibility. Because it takes the shape of its container, if I were to compress that container, let's say if that gas was inside of a syringe, I could compress that, and the gas would then assume the shape of that new volume. And the motion of the molecules is very free. They are very high speed and moving all over the place and just bouncing off of objects. Liquids have a definite volume, but it also assumes the shape of its container. So whatever container it's in, it's going to take that shape. The density is higher, much higher than a gas, and liquids have very, very, very slight compressibility. They're not really considered compressible. And the motion of the molecules is that they can move past each other freely, but those attractive forces are enough to hold them in place still and not allow them to completely escape from the other molecules or atoms. Solid has a definite volume and shape. No matter what you put that solid in, it's going to maintain that shape and that volume, no matter what container you place it in. Has a higher density compared to the other two, the highest, and is pretty much incompressible. You can't compress a solid. And solids do have enough kinetic energy to vibrate about fixed positions, meaning that they stay in place, but there is still some vibrational energy there. I'm going to end this series of notes with one more animation here. This diagram shows a source of heat underneath this container that has an ice cube in it. This is supposed to be a solid right now. And then on the right-hand side, we have a thermometer that's measuring the temperature in degrees Celsius, and it will continue up to this line which marks the 100 degrees Celsius mark. So I'm just going to put this in motion right now. So we can see that you have vibrational motion happening with the particles inside of this solid, and then as this begins to melt, we're adding energy to it. So this is endothermic energy is going into the system, and we see those particles begin to move a little more quickly in the liquid phase, and that was at 0 degrees Celsius. I kind of missed that. And we continue to add energy, continue to heat this substance. Those particles, that kinetic energy increases even more to the point where a particle or particles are eventually able to break free of that volume of space that liquid is occupying. So once we get to the boiling point, 100 degrees Celsius, we start to see particles go from the liquid to the gas stage, and they're continuing to add energy here in this diagram, and we'll go ahead and we'll let this completely boil away and let all those particles go into the gas state. And so you can see that the increase in kinetic energy of the particle itself overcomes any attraction that they have to each other. They either just bounce off each other or zoom right by. So that ends this series of notes on the change of state or phase changes of substances. And the next set of notes will start to look more closely at the terms endothermic and exothermic and what it really means to have an endothermic or an